So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're joined by Kevin Zahnle, who comes across to us from NASA Ames. Kevin got his BS from McGill University in Canada, and then went to Michigan, Ann Arbor, to University of Michigan for his PhD. He is an expert on many different areas of planetary science. Indeed, his previous talk in this series was on the moon forming impact and its effect on the Earth. So go back to our YouTube video on that. It was a very interesting talk. Kevin's true love, perhaps, is atmospheres, and that is what he's going to talk to us today about. He's been a civil servant at NASA Ames since 1989, and his interests have led him to win the NASA Exceptional Medal for his work on the comet Shoemaker-Levy 9. And today he's going to talk to us about what I think is the most important issue for Martians right now. Are they, in fact, swimming in methane or not? So please join me in welcoming Kevin.
Thank you, Adrian, for that warm welcome. The question of methane on Mars has been around a while. It's been discovered many times. The first time methane was discovered on Mars was in 1969 by the Mariner 7 spacecraft. I should mention I have co-authors. This one's me. This one's Richard Friedman. He did all the real work. This one's David Catling. He did all the thinking. And he found this. Okay. Methane was first discovered on Mars in 1960. This is too much feedback, eh? And by Professor Pimental of the University of California at Berkeley, using the Mariner 7 spacecraft. There's a bit of a backstory behind this discovery. While you read the story, it's quite a fine story. That he had been given some money by JPL to do a study of an infrared instrument. This would have been the first infrared instrument ever sent to Mars. And he was given a little study money, and he thought, well, you know, probably the best thing to do is just to know how much it will cost to build it, is to build it. So he just built it and delivered the instrument to JPL, having built it out of the study money. JPL was livid. They had expected it to cost a whole lot more. They were quite unhappy. They took it apart. They found all the UCBs on it, and they erased them and put it in JPL, so that it was then, I guess, they could send it. Since they didn't know what they were looking at, they go by, they do this flyby, and then the information is sent back to Earth, and they get a tape handed to them at JPL. They drive home to Berkeley. They do an all-nighter looking at the spectrum. And like the next day, they have to go back to JPL and do the press conference about what they discovered. Because in those days, NASA was kind of on the faster, better, cheaper mode. So they just moved quickly. So the low-hanging fruit was he had spectral lines at 3 microns and 3.3 microns. And the obvious things were ammonia and methane, and they announced that at the press conference. Two gases intimately associated with the origin and existence of life, methane and ammonia, had been detected in the Martian atmosphere. That was his interpretation after the all-nighter. The methane and ammonia were detectable only over the South Pole region, implying that the sources of the two gases were localized there. His findings produced a general gasp among scientists. The interest in methane and ammonia has been very great for very long. It turns out, though, that it was actually CO2 ice, a solid. And they figured that out within a week or two. And so the science paper, which was 2 months later, only briefly mentions this press conference and this initial misidentification. And it turns out it's just that CO2 does have features at these wavelengths. More recently, there have been 5 more reports of methane on Mars. These have been more durable. They've lasted more than a week or two. They first popped up in about 2003 when Mike Mumma gave a DPS talk. But nothing was published at the time. Other people who had data that could be analyzed got papers out immediately and beat Mike to press. From Mars Express, which is a spacecraft in orbit around Mars, Formisano et al. Reported the discovery of methane using a low-resolution spectra from Mars's orbit. I'm going to show you all these data as we go through the talk. So this, you don't have to take my word for it. You can look at it and draw your own conclusions. They're looking at the Q branch of the new 3-band at 3018 inverse wave numbers. 3018 wave numbers, which is 3.3 microns. They were seeing it between 0 and 60 parts per billion, and in a 2008 paper, they have about a 4-year baseline of this. So you see the methane coming and going, spatially and temporally variable over days and weeks, but present for, it should be 4. I should have 4 there. 14 plus or minus 5 parts per billion was the average. So it's always there, but it's coming and going very quickly. So it's being consumed, it's reappearing. A dynamic methane cycle is implicit in these data. From the first of the ground-based papers was Krasnopolsky et al., and they were using the Canada-France-Hawaii telescope. That's what CFHT means. And FTS means Fourier Transform Spectrometry. But on these slides, you don't have room to write all these words out, so you just put down the acronyms, and it makes you look like you're an expert. These are very high-resolution spectra. They looked at 15 different lines. They detected one line of the P4 multiplet of the new 3-band, and they claimed that there was 10 plus or minus 3 parts per billion. This was in February of 2003. Krasnopolsky et al. Did not address the variability of the methane. In fact, Krasnopolsky emphatically does not believe that methane is variable on Mars. The most famous paper was by Mike Mumma and his colleagues, also ground-based, using the infrared, what IRT? That would probably be infrared telescope facility? Okay. Seashell. I don't know if that's an acronym or not. I guess it must be. See, we're already you're appreciating we're rapidly reaching the end of my knowledge of these things. That's why I put up these. They make me look smart, right? Seashell. It's a ground-based stuff. They look at the R0 and R1 lines of the new 3-band. We'll see these data as well as they come up. They saw 20 to 30. They report 20 to 30 parts per billion by volume in January and March of 2003 on 5 dates. And they reported it was spatially and temporally variable, was the methane, over weeks and months. And it hasn't been seen since by Mike Mumma's group, except for a report of a different methane line in the P2 doublet of the new 3-band. This was in May of 2005 and only over the southern pole. Kind of very similar, really, to what Pimentel is reporting in that sense. No estimate of the volume mixing ratio was given in that paper. And this is buried in the supplemental online material, by the way, to the science paper. You won't necessarily know this is here. You've got to go look for it. But this is their other observation, so that makes 6. And then there was some space-based data mining of space-based data. Data mining of space-based data. That really doesn't sound very articulate, does it, Kevin? Data mining of TESS archives. The TESS is thermal, what is it?
Emission spectrometer.
Yeah, okay, good. And it was in orbit around Mars in, I think, circa 2000. Do you know what years it was?
1997.
Okay. Somebody knows. But this is data mining. So they go back to the old archives and they dig out methane in a different branch. This is at 7.66 microns, different line and a different vibrational level. There's very low instrumental resolution at those wavelengths, and there are very few photons. So digging this out is difficult, and there are other lines of CO2 and water in that same passband. So the identification of methane is not unique. The reality of this identification it requires as a prerequisite that these other guys are right about the methane. If methane is there, then the data mining in principle can be used to map it over several years. But if it's not there, they're not looking at methane. And of order 10 parts per billion, spatially and temporally variable over weeks and months, repeating over years. So I want to start with the reason why you should think this is extraordinary. Transient methane on Mars is an extraordinary result. Known gas chemistry predicts that methane has a chemical lifetime of only 300 years in the Martian atmosphere, of 300 years. That's not the sort of thing that will be variable on weeks or days or months. It would just be well mixed, and it would be the same every time you looked. And now I have to digress on a point of philosophy and language. We're scientists. Scientists agree data trumps theory. This is the scientific method. You got a good theory, you got a good data, the good data wins. Straightforward, right? We all know that's the way this goes. That's the scientific method. So now we have some words. Telescopic and spacecraft observations. The word is observation. That's what we use to describe data that come from telescopes and spacecraft. That means we categorize them in our own minds as data, and therefore we categorize them as good. Meanwhile, atmospheric photochemistry models, ding, 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 the alarm bell rings, that's theory, that's bad. Therefore, observations of weird behavior by methane trump ivory tower photochemistry models that can't explain this behavior. Right? That's your prejudice. Seeing is believing. Theory must be wrong. Not this time. The fault is in our words. The observations are not that. They are not what you think. They are not simply a raw record of what came in the telescope. They are reconstructions that depend on theoretical models. You build a complicated theoretical model of atmospheric transmission through Earth's atmosphere. These models are clearly complicated, but they have not yet been fully documented. Now, for the spacecraft observations, there's a complicated atmospheric model for atmospheric transmission through the Martian atmosphere. These are complicated models. They're not simple and they're not well documented. It's not clear that the reconstructions would be reproducible. I don't think I could reproduce what other people have done. We've attempted to. On the other hand, the photochemistry models, which is the theory, which is bad, are actually nothing but self-consistent applications of experimental data to Martian conditions. Data, they go in the lab, they rack two things together, they record the rate it reacts. And they put it in a compendium. The results are so reproducible that one cannot get funded to work on the problem. Don't ask me how I know. Results from a Mars photochemical model are very close to their foundation in experimental fact, but the reported observations may not be. There are many critical evaluations of reaction rate data in the literature, and I'm going to just show an example. There are hundreds of pages long, these tables that look like this. The need for these data stem from the economic importance of ozone chemistry and, to a lesser extent, but more recently, methane, because methane is a greenhouse gas. We care about these things. So this is, for example, evaluation 14. This is the front page, and it goes on for hundreds of pages with all of these reactions out carefully and completely annotated. You can go look at the footnotes for half a page on each reaction and so forth about where the data come from. They be data. Now, if you just put all these data together and you call it a model of the Martian atmosphere, and the Krasnopolsky is an example of this, you work out what is the methane lifetime. Methane can be photolyzed by Lyman alpha photons. It can react with hydroxyls or atomic oxygens or excited atomic oxygens, and these are the loss processes of methane. Count them up. Count up the rates. This is in one model. That's in another model, a competing model. So the one on this one would be Nair's model, and this one here is Krasnopolsky's model, and it works out 270-year lifetime in the Nair model, 470-year lifetime in the Krasnopolsky model. When I do it, I get about 200 to 300 years. So I think this is a solid result. You cannot just say this is not true. There's another thing. Oxidation of 20 parts per billion of methane in less than 1 year would overwhelm the atmosphere's redox budget. So you think of now the Mars in a global sense. You introduce methane into the atmosphere, and then you consume it. You oxidize it. Okay? If you're continually doing this, the known source of oxidants, you will get a methane oxidation rate that is 10 times bigger than the hydrogen escape rate. And the hydrogen escape rate is the only known source of oxidants in the Martian atmosphere. It's water photolysis followed by hydrogen escape. So water absorbs an ultraviolet photon, breaks up, pieces react a while, and then an H leaks out the top because hydrogens are light. And they're always rising to the top, and then they rise out into space. Because this is so big, this methane oxidation term, that is required to explain variable methane at 20 parts per billion, it would consume all the oxygen in the Martian atmosphere in 7,000 years, which means you're at a very special time if you're looking at Mars and seeing oxygen in its atmosphere. But it also causes another problem. In order to keep the oxygen in the atmosphere, you have to invent an unknown source of oxidants to balance the methane, which is also 10 times bigger than the known source of oxidants. So you have two separate things you've done. This constraint also applies to imaginary surface reactions. If you imagine that the methane is reacting on a surface, this global picture still holds because it's the whole global atmospheric redox budget you're looking at. And that includes the surface reactions. That includes reactions in dust grains and air. It includes reactions in electric discharges. You could have lightning. It doesn't matter how you're consuming the methane. When you consume methane, you consume oxidants. You need to supply the oxidants from someplace. Since you can't get them from the known mechanism, you got to invent one. So you have to invent a source of oxygen to balance this methane that you have thought you've seen. A third problem is that inventing hyperactive methane didn't solve any other problem. There was no outstanding problem on Mars that required that everything you knew about atmospheric chemistry of Mars be wrong. Because if you're introducing a term 10 times bigger than all the known terms, you're saying that everything you knew about Mars' atmosphere was wrong. But in fact, models don't have any trouble whatsoever getting the basic composition of the Martian atmosphere. The three photochemical products in the Martian atmosphere are oxygen, carbon monoxide, and hydrogen. The green is the measured amount of hydrogen in the Martian atmosphere. The red is the measured amount of carbon monoxide in the atmosphere, and the gray is the measured amount of oxygen, O2, in the Martian atmosphere. We have a free parameter here because nobody ever does a model without a free parameter so that you can make these XY plots because you got to have the free parameter being your x-axis. But there's only the one free parameter in this model, and that is the rate at which oxidants are consumed by, say, reduced iron on the surface or sulfur. And the successful models are in this range where you take oxidants out, and the oxidants being removed are hydrogen peroxide and ozone. If you choose this range for a removal rate for those guys, your model predicts the H2 right, it produces the CO right, it produces the O2 correctly, and this is the hydrogen escape rate, it gets the hydrogen escape rate. It's purple right in there. So the model had no trouble at all. Works just fine. We didn't need to introduce something 10 times bigger than the things we know about. So this is why I got interested in the problem. Is they were saying that everything we knew was wrong, and I don't think so. How about physical sinks? If you have physical sinks of methane, you don't need to have a consumption of oxygen. You don't have to worry about this atmospheric redox problem. Some of the possibilities are, one possibility is adsorption. This is where the methane just sticks to the surface or goes into some little tunnel and gets caught inside. The answer to that is no. Methane is outcompeted for adsorption sites by water, hydrogen peroxide, carbon dioxide, and even xenon, all of which are more abundant than methane has been reported to be. So methane is not a good target for adsorbing because any good place to adsorb to has already been adsorbed onto by these guys. Theclathrates? No. Kinetics are very unfavorable for theclathrate formation at these low temperatures. That's an experimental result. Somebody A fun experiment I ran across was somebody tried to convince xenon to make a clathrate at 170 Kelvin. They did it at 195 Kelvin, you put xenon in with the water ice, and boom, you get a clathrate. So they went down to 170 K, and the xenon just sat there as a liquid on top of the ice. Nothing happened. Because you have a kinetic inhibition, you have to change the structure, you have to open the cages of your ice to make the new cage that a clathrate is. The clathrate has a different, the structure of the water is a little different shaped cages. And then the xenons or the methanes go into the holes, into the gaps in the cages. So you would have to rearrange the structure of the water ice, and once you get temperatures below 170 K, the water ice doesn't want to rearrange. Methane clathrate's not stable at Mars's surface, which is why it's popular as a source. But that also means it doesn't make a good sink. Carbon dioxide clathrate is nearly stable at the Martian poles. But the CO2 methane ratio is actually higher in a clathrate than it is in the air. So if you removed all the methane in a clathrate, you also removed all the CO2 from the atmosphere of Mars, which is manifestly not so. And finally, xenon clathrate is actually stable on Mars. It would just sit there. But xenon happens to be in the atmosphere. It's not in a clathrate. So clathrate's not going to work for methane. And of course, biology. Biology is extremely attractive, as we know, but carbon monoxide is abundant at 800 parts per million, not billion, million. Methanogens, the ones we know of, can use CO both as energy source and as a carbon source. They can eat it. They eat water with carbon monoxide. So it's sort of like, you may remember years ago there was always, you'd get on one of those weird late night radio shows and you'd hear somebody calling in about how the government is suppressing this new development where you could put water into your car and drive. You replace the gasoline, you just put water in, it's free. If the atmosphere were made of carbon monoxide, that would work. You could use water as your fuel. Active biology in communication with the atmosphere does not work as a source, because if active biology were in communication with the atmosphere, it would eat the carbon monoxide in the atmosphere and would pull it out. You wouldn't have carbon monoxide in the atmosphere of Mars because it's food. So active biology is not communicating with the atmosphere very effectively. That doesn't mean you can't have active biology that's not communicating with the atmosphere as a source, but one can imagine many possible sources. It's not a hard thing to do. And so I don't talk about the sources of methane. There are many possibilities. At 10 parts per billion, methane is certainly not abundant enough to be food. It's not eaten in the Earth's atmosphere now, and it's 2 parts per million. To pull methane into the surface in 4 months requires that 1 of every 100 methane molecules to reach the surface gets eaten. So you have this picture now of the surface of Mars covered with gaping mouths, waiting for a methane molecule to come in. That's not realistic. So active biology will not work as a sink. So let's look at the evidence. I have made my views known about the how likely it is that how well methane fits in with theory. So let's look at the evidence a little more closely. These are the Mars Express data from using the planetary Fourier spectrometer. This time, helpfully, I wrote it out so I could see what PFS stood for. And you've got 3 curves here. The black curve are the data. So that's this black curve here. The red curve is their model without methane. No, wait. Which one is which? The red one is the model with the methane. Okay, so the blue one is the model without the methane. That's this one here. And so this model, it is a model, has a lot of methane in it, 60 parts per billion. It's the most actually seen in any report. But I think they cherry-picked their example. The typical example, right? You go for the single best one you've got as your typical example, and that's what this would be. There's a lot of water vapor here, too. This is well above the normal for Mars. And there's an isoptical depth of about 0.45. And there may be other things in their model they don't tell us about. But that's what they're doing here. And this is from Geminal, 2008. Now, hello, come, there. We made a Hytron model, did Richard Friedman, of that part of the spectrum. This is the methane band that they're going to be looking at in black. And all these red things are water lines. Here's some carbon dioxide, and the green stuff on the bottom is ozone. What we did is we just made a little model of Mars where we put these things in. Water, ozone, and CO2 at their known abundances, and methane at their reported abundance. They compare that model to their data. And you see here that this is the part where they think the methane is. And they think the difference between the red and the blue, that's their methane right there. But the methane band actually extends over that region. So it's not a perfect fit. The Q branch is, as a schematic, covers about this region. And that's the part that they're going to fit. So the blue, not as good as the red, but as the black right there. That's the actual data. So it's one hot pixel. One data point here that they're interested in. But if you look at the model, you see it's not doing all that well at other places either. This is the same order of magnitude of discrepancy. There's one over here as well. So the methane did provide a slightly better fit at 3018. But the model isn't really very good. It's missing the data by the same margin over here as it is over there. And this is their best case, as best I can tell. So I'm not very convinced. I find it unconvincing that they have seen methane here. Ground-based observations of Mars are kind of like this. This is my little toy. You got to look through Earth to see the Mars, right? They offer higher spectral resolution. A problem with the Geminal and the formosonal stuff is that they go in with a known wavelength, 3018, and they say, well, what can we find at that wavelength? They're not actually, they don't get a second wavelength of methane. They just got the one. The ground-based stuff has a higher resolution, and you might have a better shot at identifying a spectral feature as actually methane rather than, say, water or something else that you might have. But one must look through the methane in Earth's atmosphere, which is pretty abundant, and other molecules in Earth's air. Now, the way this is done is you look at Mars when it's advancing or retreating. So when it's coming towards you, it blue shifts the line out a little bit out of the Earth line. And when it's moving away from you, it red shifts the line a little bit out of the Earth line, and you have a chance to maybe see it in the edge of the Earth line. So you shift the Mars methane lines out of the cores of Earth's methane lines. So an example is Krasnopolsky from 2004. This is his report of Mars methane. This is the transmission through Earth's atmosphere. This is the side of the methane of Earth. And so what he did is, what Krasnopolsky is used to a straight line through here, made the difference, made this little wavelet diagram, and concluded that this bump here was a signal, while these other waves are noise. To give a better picture of what he's doing, is we made a little model of transmission through Earth's atmosphere. So this is transmission through Earth's atmosphere in our model that Richard Friedman made, to be specific. These are the telluric P4 lines of methane. It's a quadruplet. There are 4 main lines. You blue shift them because you're observing Mars when it's coming towards Earth. And of those 4 lines, one of them got blue shifted over here, and you have a chance to look at it. That's what Krasnopolsky is doing here at this wavelength. But I have a bit of an issue with what it looks like. This is clearly instrumental ringing. It's not real. So the wavy part's not real. Should I believe that he has a signal? I don't think I should. He also looked at 15 lines in this, 15 different methane lines, and he only detected it at 1, and he reports it as a 3 sigma result, which I think mathematically is correct. That's what noise would be, a 3 sigma result, if you see it in 1 out of 20, in 1 out of 15. So it's not very convincing either. The one that was convincing, apparently, was the one reported by Mike Mumma in 2009. And I reproduced here figures 1A, 1B, 2A, and 2B and lined them up so you can see what's going on. This is the slit, these two parallel lines here. That's Mars at that time they were looking. These are spectra at these different latitudes, different locations on the... These aren't really spectra. These have been severely... I'll talk about that. These are not the raw spectra. But they are what they have recovered from the raw spectrum. They plot these things up, these little notches here, they call the methane, and they plot them up, and they get an intensity profile like that, or a strength like that, a linear gradient across the disk, which they then interpret as being part of the Martian atmosphere. So the path length through the Martian atmosphere will be longer towards the poles because it's a slant path, right? And so you need less methane at the poles and more at the equator to get that curve. And so that is their recovered methane profile. So what they actually see is a linear gradient across the disk. What they report is that. So it's there's a big blob of methane that came out of the ground somewhere around in here, just north of Hellas. They reported 5 detections. This is one of the 5. Now, I'm going to tell you a little more now about what they did. This thing up here is a model, that thing you saw on top. That's their model of the transmission. And what they did is they took the model and they subtracted their data from the model to get a signal. They didn't divide because that would lead to trouble, so they subtracted. So they took a difference between a model of Earth's atmospheric transmission and what they saw in their telescopic data, and they recovered these things. And they multiplied this shaded region by 25, so that's why it gets all bumpy in here, is that they've amplified it by 25. Well, overall, it's amplified by 10. And this is their recovery of a methane line, and they detected at all latitudes they looked at. And this is at another wavelength, the R0, taken on a different night. They put them together to make it look like they've got a single spectrum, but they don't. They can only do one of these a night. So they did the R0, and there it is there. So that's what they saw. This is a synthetic construction to create a spectrum out of these things, or possible, a spectrum-like thing that you can look at. It's very interesting. Now, one of the things they report is that these are the 5. These are 4 of the 5 observations here. And these are the recoveries of latitudinal methane, plotted up as Doppler shift. And what I found immediately that caused me a little worry, made me ask questions, is they only saw the methane in blue shift, but they didn't see it in the red shift. So these 3 cases are all in blue shift. These are the velocities of approach of Mars to Earth. But when they looked in red shift, when Mars was receding from the Earth, they got nothing. And that made me ask the question, well, maybe there's something about the spectrum of methane that would cause cause one side to look different than the other. And if you look in detail, you find that there is such a thing. So for example, for the methane C12, carbon has 2 abundant isotopes, carbon 12 and carbon 13. Carbon 13 is 1/90th as abundant as carbon 12. Or put it another way, there are 90 carbon 12s for every carbon 13. So you make a methane out of carbon 12, and this would be the R1 line. There it is. Sitting right next to it is the R2 doublet of 13 CH4. So it's just sort of sitting right there on the blue side. So here you got this line, isotopic methane line, that's blue shifted slightly from the main methane line. And the same is the case for the other line they looked at. The R0 methane C12 has the R1 methane C13 on the blue side. It's sitting there to the left. And you might notice these little lines here to guide the eye. As we pull back and look at them, you see that here's the center of the terrestrial C12 line. I line it up with C12. The terrestrial C13 line in Earth's atmosphere lines up with their purported Martian methane. The same goes over here. You look at the C12. On the left of it, you got the C13 line. You line it up, and it lines up pretty close to their reported Martian methane. This is a difficulty, a puzzle, and they don't mention it in their paper at all. It's a very big signal because it's a much bigger than the Martian signal that they purport to see. So we built a model of our transmission through air of these two lines. This is the R0 C12. There's the R1 of C12, and this is the terrestrial transmission as we've modeled it. And you can see that there's the telluric C13, and there's where they think they saw the Martian methane. They differ by that much. That's the Seashell Resolution, the resolution of the spectrograph that they're using. So these things are closer together than their resolution. So they need to get super resolution to pull this Martian line out because it's cohabiting the same resolution element as the telluric line. Same over here, but the telluric lines and the Martian line are closer together and well within the Seashell resolution. So there are isotopic methane lines on the blue wings of both the R0 and R1 C12 methane lines. They are not resolved by Seashell from blue shifted Martian 12C methane. And there's a lot more of it. If you just do the numerology, Earth's atmosphere is 1.7 parts per million of methane, which corresponds to 1750 micrograms per square centimeter in a column. Earth's HYTRAN, they're using the HYTRAN methane C13 amounts, you get 20 micrograms per square centimeter of C13. The Martian methane, if you allow for 2 passes through the Martian atmosphere, the photon comes from the sun, goes through the atmosphere, bounces off the surface, goes back to the atmosphere, then through Earth's atmosphere to your telescope. So you've got to be 2 paths. And you give them 30 parts per billion, which is as much as they ever claim. It's about 1 microgram per square centimeter. So they have to look through 20 terrestrial C13 molecules for every 12 C13, every C12 methane that they see. So they are correcting for the telluric isotopic methane. They have to be because they've gotten the signal down by 1 part in 20. But they have to be able to do this correction at better than 1 part in 20. When I mentioned earlier that the C13 line is actually irresolvable from the Martian C12. There was no description in their paper at all of how they corrected for this, and we're waiting for that. I want to see how they did this, because this is this strikes me as being very difficult. Because the difference is a factor of 20. They got to remove a contaminant signal which is 20 times bigger than the signal that they intend to recover. The other reported methane line was the May 2005 detection by Mumma. And this was of a different methane line, the P2. This is not actually a very good line to look at, as I will show you in a moment. It's not as good as the R0 and R1. I got this. I wanted to know what the geometry was. It's like I was a little puzzled as to why they see CO2 lines in the northern hemisphere and not in the southern hemisphere, which is odd because CO2, the Martian atmosphere is made of CO2. You would think that they would see CO2 in both the northern and southern hemisphere because CO2 is present in both hemispheres. It's the gas of the atmosphere. So I was really pretty puzzled by that because they're seeing CO2 in the north and only in methane in the south. But if you look at the particular date they were looking at, Earth is at its most southern declination in the Martian sky. It's at its most southerly point. So you're getting the largest path lengths through the northern area you could get, and the shortest path lengths through the southern area that you could get. So perhaps that explains why they're seeing CO2 in the north, but not in the south. As to why they're seeing CO2 in the south, CH4 in the south, we should discuss that now. We made a model of this one too. The P2 line is a doublet. Notice there's no C13 issue here, but the C12 lines are a doublet here, the purple. And when you blue shift them at the amount that they looked at on May 30th of 2005, it's like 11 kilometer per second blue shift. So here's the blue. And you got a shot at this one. This one's still, this component is sort of in the core of Earth's line, and you wouldn't think there's any chance of seeing it. But this one got about 30% transmission. So you have a shot. Unfortunately, there is a water line right there. And as you know, water in Earth's atmosphere is not a very constant gas. It varies a lot from place to place, day to day, hour to hour. So we will map it up. They see these three lines. There are these three lines of CO2. They're isotopic CO2 lines. They're made out of 16, 12, 18. So they're using a minor isotope of oxygen. And R23, R24, and R25 are different rotational levels. And the purported Martian line is these guys, this doublet here, sitting right next to the R24. This is done with a model assuming 20 parts per billion of methane on Mars, which is the kind of number they're talking about for Mars. You can see that the R23 maps nicely. The R25 maps nicely. The R24, they can't see it because it's in the middle of the methane line, Earth's methane line. But the P2, they think they can see in the southern hemisphere. But there is a problem with that water line, this water line, the one that lines up with the P2 lines. This water line is 6 times stronger on average in Earth's atmosphere than the Martian methane line. So you got to remove this line in Earth's atmosphere, which is 6 times stronger than the Martian line. But there's a real problem. Water is not very constant in Earth's atmosphere, and this line in particular, unlike most of the water lines we've been talking about, this line is extremely temperature sensitive with this high temperature coefficient. So the strength of the line goes as the exponent of minus 2890 divided by T. So your model had better get T exactly right. Otherwise, you're not going to be able to correct for this thing.
Kevin, when you talk about the strength of the water line, are you talking about from Mauna Kea or from the ground?
No, from Mauna Kea.
Okay. Big difference.
Yeah, we tried to be fair. I mean, we did use Mauna Kea as the place where we worked from. That's still, that's a nice, tight, narrow line that happens to be in a very bad place. And I just don't think this is a possible thing for them to do. I don't think you can build a model without having good information on the water profile in the Earth's atmosphere and the temperature profile of the Earth's atmosphere at the very time you took the observation to be able to extract that. They don't have another line which is this temperature sensitive. So you can't go look at another water line and say, it'll behave like that one. Because this one does, that one's different. Oh, summary time. We're almost done. You have made it through this. I haven't given the talk in a while, so I was kind of surprised here too. Short-lived abundant methane on Mars is extraordinary. Known chemistry predicts a 300-year lifetime. They're claiming from their observations that it's weeks or months. And I put quotes around observations because I want to emphasize that they depend on the model of transmission through Earth's atmosphere and their model of transmission through Mars's atmosphere to deduce these observations. The atmospheric redox budget precludes persistent, short-lived 10 parts per billion of methane. So if you just went with Mike Mumma's observations, it's basically a one-off. They haven't seen methane since, so it does not preclude his observations. Because it appears that if you accept Mike Mumma's observations, it's just, there was this plume. There were these plumes at one time at one place, but they don't happen often at all. In which case, you don't run up against the redox budget issues. But if you accept the spacecraft observations, they do. And you require, and one of the reasons people have bought into methane is that there were these independent reports. Spacecraft observation, ground-based observation, independent. That's been important because no one would probably take them that seriously as an individual report. But that there were more than one report getting the same kind of answer seems to be more impressive. But if you accept that the spacecraft observations are telling you anything useful, you would then conclude that it's persistent, in which case the atmospheric redox budget also precludes what you're seeing. Because you need an unknown source of oxidant, you need also, this argument applies to surface reactions. So if you invent an unknown reaction, which you would do to get around this problem, because the known chemistry is atmospheric chemistry, so you need to invent some new chemistry. You invent new chemistry, but that's still subject to the redox budget issues. You have to go into transmutation of elements if you want to get around this one. Adding methane in its unknown oxidant at 10 times the levels of the other forcings in the Martian atmosphere creates new problems without solving any old ones. There wasn't an outstanding problem that methane was going to solve. Methane is just a one-off. It's out there. It's this observation looking for a purpose. None of the reported methane detections are convincing. The Mars Express results are very low signal to noise and model dependent. And really devised to record to account for a single pixel in their instrument. The IRTF Seashell, this would be, the IRTF Seashell, which is the Mumma stuff, cannot resolve the strong telluric isotopic methane lines from these weak blue-shifted Martian lines at R0 and R1. R0 and R1 are the right wavelengths to use. Mumma is looking at the right ones, but he should look at them in redshift. The P2 doublet coincides with telluric water. I don't think the P2 doublet's a very choice place to look. The reason you look there is that it's a fairly weak line, and so the terrestrial absorption is smaller. So that was the hopeful part. But the problem is that it's a doublet, and then you got this water issue. Redshifted R0 and R1 lines of methane are cleaner. But for these, the published observations all imply an upper limit on the order of 3 parts per billion. No one has detected the methane at those wavelengths which are most suitable for looking for methane. Addendum, the postscript. The Mars, oh God, what is MSL? Mars something or other something. Let's have a vote. Science lab, not surface land or whatever. The Mars lithospheric breaker. The MSL carries a well-conceived methane detector that can detect a part per trillion. I bet you this. They eventually drop off from that. That's on the hopeful side because I've been, there was this Office of Inspector General report, la da da, about contaminants. It makes me think that a part per trillion was probably a little more hopeful than they'll get. Nevertheless, that's 10,000 times better than you need. So even if they get 10 parts per trillion, they'll nail methane with a very well-conceived experiment. They're looking at this very small piece of wavelength where you've got a triplet, the C12 R3 triplet here, which is distinctive. It's got this little pattern. So you have a fingerprint. If you see this little pattern, you're seeing methane. You're not just looking at a single line that coincides with a tabulation of lines in their frequencies and saying, I can line these two up. I'm going to call it methane because they line up. But you have to have more than one line if you want to actually claim, I've detected methane rather than detecting a signal at a wavelength. You have 3 lines here in a distinctive pattern. You detect that, you have detected methane. But the experiment's even better than that. They can get C13 too, with another very clear little pattern, quite distinctive. That's the R4 of C13. And to top it off, they get deuterium sitting in the same little box. This is probably an R0 or an R1. This is pretty cool.
Kevin, shouldn't that be CH3D?
Yeah, it should. I'll fix it before it goes up on the web. As soon as I'm done while taking questions, I'll be editing that slide. You're quite right. That is not some new molecule at a CH3D. So this pleases the Webster and Mahaffey, who built the instrument, to be reminded they can do this. So if this thing actually manages to get to Mars, land, and work, the Mars methane question will have been addressed at the level necessary by next year, around this time.
Unless it's episodic?
Well, I don't know how you're going to get rid of a part in, you got to get down to a part in 10,000. Even episodic is going to have a hard time with that. I mean, at this level, you're thinking they'll probably get the methane from the Viking light detection experiments. I mean, if they don't see methane at a part per trillion, it's really not there. And they probably will see it at a part per trillion. I mean, it's pretty hard to imagine any planet so clean of debris and weird molecules that doesn't have a part per trillion of a molecule like methane, which is a pretty robust molecule. Very simple. I mean, I'd be quite surprised if it's not present at that level. But this is not the level that's being talked about. 10,000 times smaller. I'm done. You've made it. Thank you. Okay.
Can you go back to the Theclathrate explanation?
Yeah.
You mentioned that there would be a linkage between the CH4 and CO2 clathrates.
Yeah.
That, can you explain?
Yeah, the way clathrates work is that you start making a clathrate, then everybody that can go into a clathrate goes into the clathrate according to their own desire to be in a clathrate. So once, say, xenon or hydrogen sulfide or SO2 starts the clathrate bandwagon going, you've got some clathrate. Then if there's CO2 around, it can go in there. If there's methane around, it can go in there. Even if methane by itself would not make a clathrate, methane will go into a CO2 clathrate. So then you ask, okay, if that's the way the clathrate's working, and I want to remove all my methane in a clathrate, that means I'm removing all my CO2 in the clathrate too. But I'm not doing that because Mars keeps CO2 in its atmosphere.
Thanks. Is the Mars Science Lander or Science Laboratory a lander or an orbiter? Will it be able to settle the question for all the locations on the planet at which methane is supposedly been seen, or just where it lands?
No, that is the purpose of the Trace Gas Orbiter, known as the TGO, is to do a global survey. And their approach will be to use a photometer, a spectrometer that looks at the sun. So you're always looking at sunset or sunrise, and you're looking through the atmosphere at the sun. It gives you lots of signal to noise. And then you look for absorption by some trace constituent through this long path length, the grazing path you get when you look at the sun at sunset and sunrise. And that also can get, I think, 1 to 10 parts per trillion for methane. That's planned on the TGO. It's kind of thing you want to do if you want to map methane plumes erupting and getting destroyed and that kind of thing. But their TGO has other purposes. It will also map ozone and HO2 and water, things that are of great interest to the GCM community and for the current climate of Mars. So it has other purposes, but it's true that methane was kind of a driver for that mission. The MSL is just a lander and a rover, and to drive, I don't think they'll drive everywhere on Mars in the course of 1,000 years. And by that point, the plutonium will be dead.
So I have a speculative question. Say the transient methane plume turns out to be reality and no other methane. Are there existing models that would indicate whether that subsurface methane is the result of geological processes or biological processes?
Now, sources are very easy to come up with. I could list 5 or 10 off the top of my head, so could you. It's not a hard thing to imagine sources. They're perfectly plausible for Mars. Methane clathrate's one. People have talked about serpentinization reactions as another. I think that's not likely to be right, but methane clathrate is likely. And then there's biology too, and you can think of others. Volcanoes do produce methane on Earth, just very tiny amounts. So there's no reason to... I'm not going to argue that methane shouldn't be on Mars because of the source issue. The question is the sinks, because the sinks all happen in our view. We can look at Mars and assess the sinks. They're right there in front of us. The sources are cryptic by definition, and we can't really do much with them, but speculate.
Kevin, has Mike Mumma released his raw data so that someone else can do the whole analysis?
I believe he has said that releasing his raw data to someone else would be like giving a loaded gun to a child. I will leave him at his word on that. I think that I personally would not be someone that would do a good job with his raw data, but there are people in the field who might be able to do something with it. It is true that I should not be given those data.
The C13, C12 ratio, will that be used to determine whether it's biological or chemical?
That was the, what is that thing doing in front of me? I don't want that around. Good old Microsoft. Yes, that was the plan, because when they put this thing on, I think they were less skeptical of methane on Mars than they are now. I think Webster and Mahaffey have decided it's best to keep an open mind. They put a lot of effort, and NASA put a lot of money into devising this peculiarly great experiment.
And the orbiter, can that do the same thing?
Hmm?
Can the orbiter do the same thing?
I don't know. Can it do well? Yeah. It does C13 also? Yeah, it probably crushes it. I mean, if they're measuring 10 parts per trillion from the orbiter, and it's present at 10 parts per billion, they'll probably do okay with the C13. Not great, actually, but okay.
Kind of just a background question. From a thermodynamic basis, are there known materials on Mars as highly reduced as is methane? And secondly, could you comment on perchlorate, which...
I love perchlorate.
Well, yeah, and that's obviously a potent oxidant.
Yes, it is.
And its genesis on Mars would suggest an oxidation potential that is really one to deal with.
Yeah, there are lots of oxidants. Mars has a lot of oxidants, and that's one of the reasons why the high abundance of carbon monoxide is kind of a surprise. Is carbon monoxide ought to be getting oxidized by these things if these things are currently actively oxidizing things. That they're not oxidizing carbon monoxide is, to me, an argument they're not going to oxidize methane, since it's much easier to oxidize carbon monoxide in general. There are exceptions. Chlorine, I know, does not react with carbon monoxide, but will react with methane if it's warm enough. It's not warm enough on Mars, but if chlorine can do it, there may be other things that can. Kinetics. Yeah, kinetics. Thermodynamically, the methane should react with the oxygen. Mars's atmosphere is 2,000 parts per million oxygen. It ought to react with the methane. I mean, thermodynamically, that will go. No, that's important because that's one of the, to me, that's the great hope of TGO, is that they get lucky and see SO2 or H2S coming off. In the gas, of course, although H2 is in the atmosphere and fairly abundant. But H2 is not as reduced as methane. But at the surface minerals, you have, I think, olivine minerals at the surface. They're pretty reduced. You have sitting around, you have chunks of metallic iron nickel meteorites sitting around. So you have the potential to reduce things. They're still sitting there, so they haven't been oxidized. At least not to nothing. They're still there. And there's also always pyrite. I don't know where that stands with respect to methane, though.